Okay, so here's an example of a piecewise function that I just drew. It's not too precise, but it'll do. And let's talk about different types of continuity. So we can see here at 2, we talked about how it's discontinuous at this point. And that's because we have to lift up our pencil, jump up here, and then come back down. And we call that a removable discontinuity. So the problem at x equals 2 is that the limit as x approaches 2, and let's call this function f of x, why not? The limit exists, the limit equals 4, but that's not equal to the function value, which is, what's the function at 2?
6.
6. Yeah, so f of 2 is not equal to the limit as x approaches 2. And so we call that a removable discontinuity. Basically because it can be fixed, right? So if we wanted to change this function to make it continuous, we could just sort of erase that little dot and stick it back where it's supposed to be, and it, voila, it would be continuous. At x equals 3, what's happening at x equals 3 here?
Well, it looks like there's kind of a cusp there, sharp right turn.
Yeah, there's kind of a corner. There's something happening, right? This is piecewise. I haven't told you what the function is at different points, but something's happening there. It changes. But it's still continuous because the limit, and I'm calling this x equals 3. I know that's not exact, but the limit from both sides is 7, and the actual value there is 7. So this is an example where the function is continuous. So at x equals 3, f of x is continuous. So just because we change from one function to another doesn't mean that it's necessarily discontinuous there. The two functions could sort of meet together nicely. Okay, at x equals 4, what's happening? Well, from the left side, it looks like the limit is 7. And from the right, the limit is 4. So the limit doesn't exist there. The limit from the left and the right is different, is 5. Thank you. Thank you. So the limit, that's why we have 2 of us. So the limit as we approach 4 from the left is 7. And the limit as we approach 4 from the right is 5. And those aren't the same. So again, here it's discontinuous. And this type of discontinuity is called a removable discontinuity. Or not removable, what am I saying? It's a jump discontinuity. Because there's no way to fix it. In this case, I almost want to call it something different because you're not really jumping down, you're almost falling down. But anywhere that
drop discontinuity.
Drop discontinuity, yeah, you fell down. But anyways, you're going along and then you have to completely change where you are and keep going. So that's a jump discontinuity. There's no way that we can switch the value of f of 4 and make it continuous anymore. Okay, and then the last one I want to talk about is what's happening here at x equals 8. So first of all, f of 8 isn't defined. It looks like the function that has an infinite asymptote there, right? That it's going towards negative infinity from both sides. So the function's not defined there. And so it can't possibly be continuous. That was, I think, the very first property of being continuous is the function has to be defined. So at x equals 8, what we have is a infinite discontinuity. Okay, so there are a couple different types there. We have the removable, which is just kind of looks like a hole, and you can think about that as a discontinuity that is fixable if you change the function. We have the jump discontinuity where you're either jumping up or in this case sort of falling down. And then an infinite discontinuity where you have maybe a vertical asymptote.